Just remember our so-called physics here. We just want to continue with this work and look at it for a varying force. So we've got a more generalized expression or definition of work. The definition of work done by a force, whether the force is varying or constant over the displacement, whether the force varying or constant over the displacement is work done by a force is equal to integral from some r initial to some r final of f hat dot dr hat. So this is the infinitesimal displacement vector. This is the force vector. There's still a dot product in between the two, and these are the limits of integration regarding this displacement or change in position that's taking place. So what happens if the force is constant? Well, if the force is constant, this is just a scalar quantity, comes out front, and you've got the integral of dr from r final to r initial, or r initial to r final, which just gives us delta r. You get it back f dot delta r. But if the force is varying, we want to be able to still understand what the work done by the net force is. So consider a varying net force. The work done by that net force will be equal to the integral from some r initial to some r final of sigma f hat dot dr hat. So again, what we're going to assume here, just again to make things a little bit cleaner for us, is that the force is in the displacement, in the direction of the displacement. So we'll let the net force be parallel to dr hat, f hat. Thus, if that's the case, the angle between them is 0, and the cosine of 0 is just 1, and this resolves down into the work done by the net force is equal to the integral from r initial to r final of sigma f dr. F dr. Anyways, this is what we've got going for us. Well, how are we going to do this integration to show something about this, to extract something out of it? And the answer is very carefully, because we've just said that the force is going to be varying over the displacement. This is changing with respect to its position. So this is a force that's not constant. You can't just pull it out front. So what do we do with it then? Well, we still know something about it. Whether it's a varying force or whether it's a constant force, the net force still produces the acceleration. If the force is varying, the acceleration is varying in the same sort of manner, right? So we can still write this as being the integral from r initial to r final of ma delta r, but dr. All right, good. And again, this is because sigma f is equal to ma for varying or non-varying force. But now we've got a varying acceleration. So how are we going to deal with that? We could go ahead and say, for argument's sake, that the mass is constant, which is what the realms of what we're doing here will be working with. So that could be pulled out front, but we've still got an acceleration that is varying with respect to position. So how are we going to add up all those variances, right? Well, what's the definition of acceleration? That's right. The definition of acceleration is the rate of change of velocity with respect to time. So what happens if we go ahead and put this strict definition for A in there? Well, we're going to write this then as being then the integral from r initial to r final of m dv dt dr. They say, well, you just made things worse. That doesn't look any better. How are we going to do that? The answer is, again, still very carefully. So what we've got here is the ability to start switching some things around. We've got dV, dr up on the top, dt on the bottom, right? Numerator, denominator. What happens if we just switch the order? What happens if we write this? If we write it as the integral, I'm not putting any limits yet, of m dr dt dv. Completely legal, mathematically. Nothing wrong with that. Nothing wrong whatsoever. And there's a reason that I'm waving off the limits of integration now. Because under this adjustment now, I'm not integrating with respect to position, I'm integrating with respect to velocity now. Infinitesimal changes in velocity is what I have to sort of add up, account for. So at position r sub I, we would have some initial velocity v sub I. At some position r sub f, the final position, we would have some final velocity. So we can just do a switcheroo with the limits of integration here and say, well, now I'm integrating from v initial to v final. Okay, so we switch the limits of integration. What else can we do with that? And the answer lie within dr dt. Does that remind you of anything? Well, if we change that to dx dt, what would you say that that is equivalent to? Well, dx dt would be the velocity in the x direction, right? Well, drtd is just the velocity of the object in the direction that it's moving. By definition, right? Velocity, dr dt, magnitude of velocity here. So what do we've got? Well, we can take that dr by dt there and write it as v. And now we've got the work done by the net force is equal to the integral from v initial to v final of mv dv. Well, look at this. M's a constant, and yeah, v's varying, but that's what we're integrating over. Huh, that makes that easy. What's the integral of v dv? The same thing that we'd have for the integral of x dx, right? The integral of v dv is v squared over 2. So this ends up being m times v squared over 2 evaluated from v initial to v final. Which gives us what? This is going to give us the work done by the net force is going to be equal to m v final squared over 2 minus mv initial squared over 2. mv final squared over 2 minus mv initial squared over 2, which is equal to what? That's right. Sigma f is equal to 1/2 mv final squared minus 1/2 mv initial squared, which, one last thing, no, actually 2. That's equal to the final kinetic energy. And that's equal to the initial kinetic energy. Ke final minus Ke initial, which is equal to delta Ke. So the big point with this is whether or not the net force is constant, the net force produces the object's change, the work done by the net force produces the change in the object's kinetic energy. The work energy theorem is valid for varying force or non-varying force. Net force we're talking about here. So I just want to be able to show this and say, hey, yeah, we could have complex forces varying over position / time, and we can still figure out the work done by that force and the change in kinetic energy then that object undergoes. Fantastic. So what better way to start looking at all this than doing some problems, right? I'll be in another clip. Have a great day.